operations, chief operations, and applications that will be powered by our database. Then in the second step, in conceptual database design, we aim to develop description of the data and the integrity constraints, a description that is simple yet precise. It must be precise enough so that we can later translate it in terms of a data model that's supported by the DBMS. Now, we already did this. We used the ER model in this step, and subsequently we translated the ER model that we obtained in terms of relations, since we are using the relational data model. So step 2, conceptual DB design, describe data and integrity constraints in a manner that is simple yet precise. Next comes logical DB design, logical database design. So it's here where we translate our conceptual database design to a database schema in terms of the data model, one more time, that's supported by the DBMS that we chose. Because okay, dreaming about your non-existent yet fabulous database is all well and good, but at some point you have to actually create it. You have to actually implement it with a DBMS, the database management system, if you're to actually use it. So you choose a DBMS. We are dealing with relational DBMSs right now. So you pick a relational DBMS. This means that you have to convert your relational, conceptual database design into a database schema in the relational model. And we saw this, I'm not going to write this now, we saw this ER to relational mapping. This was in the first seminar, and it was quite straightforward. Remember, this was the difficult part, right? And then this translation was the easy part, as it was basically it's like an automatic process, at least this part in particular. Now, the result, so this conceptual schema in the relational model is also called the logical schema. The one that we obtained from logical DB design. All right, next we have schema refinement. When we refine the relational database schema that we obtained in the previous step, in the first step. Right now we are making decisions that are based on the theory of normalization that we discussed in detail. What are we doing here? Now we know, we eliminate redundancy from our relations, redundancy along with its associated problems. You remember, due to redundancy, we can have insert, update, and delete anomalies. Step number 4, normalization. Now, these first 2 steps here, requirements analysis and conceptual DB design, are inherently subjective. If a researcher also has, remember this example, right? Also has an impact factor and a salary, and the impact factor determines the salary, it's true, one could model a situation with 2 entity sets. Let's say, so researcher and another entity set that has these attributes, impact factor and salary. And then you could have a relationship set among these 2 entity sets. But one more time, conceptual DB design is a subjective process. You can easily arrive at this diagram for researcher. So you then translate it to the relational model, and you get this relational schema, which you then subject to the critical analysis of the normalization theory during schema refinement, which does not forgive issues like this one. In particular, now we know, assuming all attributes are in 1NF, which they are, This is a relation that it's not that is not in the for normal form. We have this dependency impact factor determines salary. And now we know how to approach such a situation, how to treat such a case. We'll do what? We'll refine this schema by decomposing researcher into two smaller relations. In one of them, we'll keep everything minus salary. So we'll have RID, FName, LName, and impact factor. So we've removed the right-hand side, the right side of the dependency. And in the other one, in the other relation, we'll have the attributes that are part of our dependency, both the determinant and the dependent, that is impact factor and salary. And can be a primary key here. All right, so that would be schema refinement. And finally, we have a physical database design, the fifth step that we're covering now. Here we take into account performance criteria and the expected workloads of queries, that is, queries that will arrive at our system, and we further refine our design. What can we do here? We can create indexes. We can cluster table, with clustered indexes. We can even redesign subsets of the schema, parts of the schema. For instance, here, if we know that I don't know, a lot of queries will filter data based on most of them will search for researchers based on their RID. So then we have a clustered index on RID, but we also know that a lot of queries also filter researchers based on the first name and the last name together. So we might decide to create a non-clustered index with these two fields, in one order or another one. If you use first name and last name, such an index would speed up queries with conditions of the form where first name equals something and last name, for instance, greater than something, or where first name greater than something, but it would not speed up queries of the form where last name greater than something. So you must be careful how you place your columns in your search key. For B plus 3 indexes, the order does matter. As one line data is first order by the first column in the search key, then by the second, and so on and so forth. All right, so that's about it for database design. Now we'll continue with UML. Now, I know you already know about UML, Unified Modeling Language. Still, just in case you forgot, or for those of you who don't, it's basically a design methodology that's concerned with the entire software design and development cycle, meaning it's more general than entity relationship, than ER. It targets processes like conceptual DB modeling, business modeling, system modeling, and conceptual DB modeling corresponding to the creation of the entity relationship design. Now, what's very cool about it is that, just like in the case of the ER model, the elements in UML can be represented with diagrams, with different type of diagrams, can be pictorially represented, which is nice, because you get an overview, a visual overview of your system. We have, we have activity diagrams, we have class diagrams, we have use case diagrams. Now, class diagrams in particular are quite similar to ER diagrams, but apart from data entities and relationships among data entities, class diagrams also capture application entities and relationships among application entities. Now, from here on out, we're going to focus on class diagrams, and on particularly on those aspects that are relevant for building a relational database design. So the main concept here is the class. It's graphically represented by a rectangle, which is divided into 3 compartments. in the first one, in the top one, you have the name of the class. Then in the middle one, you have all the attributes in your class. And finally, in the last one, so in the bottom compartment, you have all the methods, all the operations in your class. And you know this, right, from OOP, and I think also from high school, if I'm not mistaken, that for attributes, from the 12th grade, I think, for attributes, or 11th. Well, anyway, for attributes and methods, you can specify these access modifiers, public, protected, and private. Now, we'll continue with relationships. We talked about classes. Now we continue with different kinds of relationships among the objects of the various classes. And we'll start with associations. Now, an association, as you can see here, is graphically represented by a line that connects the classes. Now, here we have two classes. We have professor with attributes CNP, last name, first name, and date of birth. And we have research group, class research group with attributes code, name, description, and budget. And we have this logical connection, this association among the two, among professor and research group, which is labeled leader. So this is a relationship among what we're seeing here on this diagram is a relationship among a research group and the professor that is leading the research group. Okay, so we could have multiple professors working in a research group, but one of them is the leader of the group. So it's this relationship that's modeled by this association that's shown in this diagram here. All right, now we also specified the so-called multiplicity. Here we have a 0, 1, yeah, meaning that a professor can lead 0 or 1 research groups. And then we have this 1 here, meaning that a group is led by 1 professor. And it's exactly 1 professor. So then, of course, we can have professors that are not leading a group, that are only working in a group, but that would be a different association. Okay, so this 0, 1 here represents the number of objects, so the number of research group objects that can take part in the association from the perspective of the professor. Yeah? And this 1 here represents the number of professor objects that can participate in this association from the research group's perspective. Now, there are multiple ways of specifying multiplicities. Yeah? You could say, so we have this 0 or 1, which means no instances or 1 instance. Or you could have multiplicity of 7, yeah? which would mean exactly 7 instances. Or you could have 0 asterisk here, or simply asterisk, meaning 0 or more instances. Or you could say 3, 10, which means at least 3, but no more than 10 instances. Now, what else do we have here? We have these role names. So apart from multiplicity, we can also we can adorn the ends of an association with other elements, like we use role names here. For instance, an example, we have leads and led by. Now, these describe the role played by the objects in the association, by research group and professor objects. So by this convention, a professor leads a group. Of course, 0 or 1 groups, we have the multiplicity, but it leads. And a research group is led by a professor. Now another important aspect here is the so-called navigability of the association. Right here, navigability. Now, the navigability of this association in particular is unidirectional, as indicated by you have this arrow here, but it could also be bidirectional, in which case there'd be no arrow, and we could navigate the relationship from both ends. If we talk code a bit, in the professor class, yeah, we could have, for instance, it could be a pointer. We could have a pointer that is called leads, a pointer to a research group object. So in the professor class, we could have a pointer called leads to a research group object. Of course, this one would be null for professors who are not group leaders, who are not leading any groups. And in research group, we could in turn have a pointer to a professor object, pointer called led by. So this means we'd be able to go from a professor to his or her research group, yeah, if any, and from a research group to its leader, to its professor. Now, our association is unidirectional, which means a research group knows about its leader, knows about the professor leading it. But a professor who's a leader does not know about their research group. So we'd have a pointer led by in a research group, but no leads pointer in professor. All right, so this is how we can read this association: professor, leads, 0 or 1, research groups. We use the class names, we use the role name, and we use the multiplicity. Okay, so this was the this first type of relationship, the association. Now let's continue with another type, that is aggregation, which represents a part whole or a part of relationship. For instance, I took these two classes, written exam with a group and the date and the definition, assuming a certain structure, and like the text for a big problem, and a class multiple choice question with attributes, text, and points. And I don't know, you could have 10, you could have 20 multiple choice questions for a particular exam. It really depends on the difficulty of the questions. So I use this multiplicity here. Now we can regard a written exam object as a whole that has multiple components, multiple parts, among which we also find these MCQs, these multiple choice questions. But the thing is that when you deal with aggregation, if you destroy the whole, its contents can continue to exist. If you destroy a particular written exam object, the MCQs, the multiple choice questions, its MCQs can continue to exist. I could have, for instance, I could have these MCQs stored in a database, and I could randomize them and assign them to different exams randomly. One particular MCQ with its text and number of points could be assigned to a particular exam. Now, if I destroy this written exam object, the MCQ, the multiple choice question, could live on. It could then be associated with a different exam object. And we represent such a relationship with this unfilled diamond, this hollow diamond on the, let's call it, on the containing class. If we remove an object of this class, its contents one more time can live on, can continue to exist. This one is aggregation. Then we have composition, which is stronger than aggregation. So in particular here, we have a faculty that can have multiple departments. If you destroy the faculty, its departments are gone. So they don't exist independently of the faculty. So composition is used, and you have this full diamond here is used when when the part cannot exist outside the whole, that is independently of the whole. A department, this is how we see things right now. A department cannot live on its own. If it could, in our context, then we would represent this relationship as an aggregation. Or if you say, let's take another example, if you have this interpretation that whenever you delete a folder, all its files are deleted, yeah, without a warning, without anything as well, then you would represent the relationship among folder and the file, the folder class and the file class. So the folder and the files, let's say, that it contains, using this composition relationship. But if you consider that, I don't know, the files are in the clipboard, you know, why not? You could see things like this, because you copied them, and then this means, okay, you destroy the folder, but the files are still in the clipboard. If that's possible, then you could represent this using aggregation, right? Because you delete the folder, but the files are somewhere in memory, and if you paste them, if it's possible to take them from memory and paste them somewhere else in a different folder, they will continue to exist. So you will have aggregation. All right, so association, aggregation, composition, and now let's also see reflexive, irreflexive association, which is simply an association that is between instances of the same class. Like we have here an association among an employee and another employee. We have the same class at both ends of the association, and what we model here is a hierarchy in a company or in an organization where an employee, particular employee, can have 0 or multiple subordinates. If he's a boss, he can have multiple subordinates, but each employee can only have 0 or 1 supervisors. Every employee 0 or 1. In particular, if you have the CEO of the company, let's say he responds to no one, although that's not really true. But if that were, that's the CEO. We can say it. We can say he or she doesn't have any supervisor. So then we'll see in a bit how we can represent this in a table, in a relational database. We'd have a different field which would point to the ID of the employee. So you can represent in a relational database this type of relationship, reflexive association. Alrighty. So we covered classes and these types of relationships among objects of different classes. Now let's see how we can translate conceptual model represented in UML to a relational database, to a relational database schema. Now, one possible approach is to go with a one-to-one mapping. That is, each and every class in your model becomes a table. Okay, it's possible, but it also has a number of drawbacks or a number of problems. One of them is that you can end up creating too many tables. We'll see in a bit that we can have situations in which we take 2 classes and we create a single table, not 2 different tables. If you have too many tables, this means you can have a greater number of join operations, and we know joins are expensive, particularly when tables get quite large. So either too many tables, or you could end up omitting tables that are actually necessary. We now know that in a relational database, to represent a many-to-many, you need an additional table. You need a join table, which you would skip in this case, were you to use a one-to-one mapping. Moreover, you would not be properly handling inheritance. We'll talk about inheritance in a bit on concrete examples. So let's first see how we can. I'll have to detach this so I can write. Okie dokie. So let's see how we can map particular class. Let's start with this one, a particular class to a table, and then we'll continue with mapping associations to some tables. One table, multiple tables. We'll see in a bit. So here we have a class Snapchat account with these attributes. We have the Snapchat URL. We have the name of the user, their date of birth, the lens. Let's say the lens that was last used, and the age of the user, which is a bit redundant since we also have the date of birth, but these are the attributes that we have here. Well, then we'll create a table whose name will be the plural of the class name. So here we'll have Snapchat accounts. So the plural of the class name will become the name of the table. Then all simple attributes in our class will become fields in our table. So URL in particular is a simple attribute. The name is also of the user, is also a simple attribute. And so is the date of birth. Date of birth. However, lens, this is why I drew it like this. Lens is not a simple attribute, it's a composite attribute. Let's say it consists of, we could take the name, and we could take, for instance, the status of the lens. So this one will become a table. I'm going to draw it in a bit. But let's continue with age. This is a derived attribute. Yeah, we can obtain the age from the date of birth. We talked about storing age and date of birth, so I'm not gonna get into this one more time. The important thing is that derived attributes like this one are not mapped to table fields. So age won't appear in our table, as this would be a redundancy. Now let's go back to the composite attribute lens. This one becomes a table, a separate table. So I'm gonna have a lenses table here with I say I take the name and the status, and then I'm going to have some key here, and I'm going to refer to this one using a foreign key here. But before I do that, I'd like to talk a bit about this concept of surrogate key. Surrogate keys are added. We actually use them a lot. Yeah, so far we always added for pirates a pirate ID, for student a student ID, for ship a ship ID. Yeah. This is an example of a key that does not come from the domain of the problem that you model. We model a problem about pirates, and the pirate has a date of birth, a reputation, and so on and so forth. They don't have an actual ID. We add that surrogate key, that primary key, which is the ID, and in general we also use that identity. So we let the system, in particular it was SQL Server in our case, we let the system automatically generate values for this key, which means we don't have to worry about it. So I'm going to use a convention, a different convention right now. You're free to use any convention that you want. Just in one diagram, just be consistent about it, okay? Or you can create another one, why not? But the idea is that it should be easy to read. You should be able to easily convey what you want to say via your convention. So this is a possible approach. As the name for the surrogate key, I'm going to use an ID, and I'm going to use this one in all the tables. So this one will be the primary key. And then as the name for the foreign key, I'm going to use the singular of the table name followed by the ID. So in my case here, I will have a lens ID. And I have, now we know that this one is in fact a one to many. Okay, so this is how we do things. This is how we transform a class into a table. One more time, the plural of the class name will be the name of the table. All the class attributes that are simple class attributes will become fields in our table. If we have composite attributes, those composite attributes will become tables themselves. And we add these surrogate keys. And if it's possible, we let the system handle them. So we use integer numbers that are automatically generated by the DBMS. All right, so this is how we map a class to a table. Let's see how we can map associations. And we'll start with associations with a multiplicity of 1 to 0, 1. 1 to 0, 1. So here we have these two classes, student with last name, first name, address, and date of birth. And we have sorry, let me just take a sip of coffee. So we have this second class DB topic with a name, with a description, with an assignment date, and with a fun level. And so a student can have 0 or 1 topics. 0 if the student has not chosen a topic yet, or 1 if they did choose a topic. Whereas a lab topic should be assigned to a single student. In such a case, we can create 1 table per class. 1 table per class. So we'll have students. And so again, it's the plural. And I'll have again the ID here, the surrogate key. So I'll have the last name, these simple attributes. I'll have the first name. And now let's suppose that address is not a simple. If it is a simple attribute, we simply say address. But let's suppose it's not, in which case we'd store an address ID here. That is the address. This composite attribute would become a different table with, I don't know, street, city, whatever. And I would have an ID, the surrogate key, and then here I have the foreign key address ID. And so I have the date of birth. Date of birth. And the second table, so it's DB lab topics with the name, the description, the assignment date, and the fun level. And what we can do here is, okay, we can add an ID, a surrogate key, and then add a student ID, a foreign key referencing ID in students, and make that column unique. Another approach is to simply add a foreign key, student ID. So this one references ID in student, which is also the primary key in students. So only this ID here will be automatically generated. And here I have a foreign key that is also the primary key of the table referencing ID in students, which means a student can have 0 lab topics. That is, that student ID does in students, they have a 1, simply does not appear in DB lab topics. They have not been assigned a topic yet. Or the student can have 1 topic because a student ID, 1 or 2, can appear only once here in lab topics. And the topic can belong to a single student, or can be assigned to a single student. Now let's continue with an association with a multiplicity of 1 to 1. Now let's suppose that you could have something like this. 2 classes, individual and DNA profile, with, I said, for instance, supposing things can be super simplified and everything can have some markers here, marker 1, marker 2, marker 3, marker 4, maybe more. And for an individual, we have the height, weight, hair color, eye color, and CMP. Now, supposing we have this 1 to 1 multiplicity, we can create, in this case, a single table that will contain the attributes of both classes. I don't know, maybe you need it for family tree or something. So I'm going to have an individuals table with an ID, that would be the surrogate key, and then the rest of the attributes: height, weight, hair color, eye color, and CNP, and the attributes in DNA profile. So marker 1, 2, 3, and 4. Or you could choose to prefix some of the attributes with the name of the, you could say DNA profile marker 1 or DNA marker 1, DNA marker 2, if you want to distinguish between these. So this is a good approach. However, if you are in the following case, it depends, yeah, on your requirements and on the expected workload of queries. If you will have a lot of queries that select only DNA attributes, so only these attributes here, then maybe 2 tables are better. 2 tables could be better as more rows will fit in main memory. So it depends. You can use the previous approach for this one as well. However, for this multiplicity, 1-to-1 as well. However, this particular approach, yeah, with 1 table for 2 classes, can also be used for when you have a small number of objects in the first class that are not associated with objects in the second class. So when we had students and lab topics, when we have a small number of students that did not get a lab topic. So here we could say, okay, instead of these 2 tables, we could have a single table. Students with the ID, this would be the primary key, and the last name, the first name, let's put the address ID, the DOB, the date of birth, and then you could say, let's say, topic, because we talked about prefixes before. You could say topic name, yeah, topic description, topic assignment date, topic fun level, yeah, and so on. So this one is good, but only if you have a small number of students without an assigned topic. Because if you have a large number of students that are in this situation, then this means that for a large number of rows here in students, you'll have null values for all the attributes that come from this class, from DB lab topic. All right, so let's continue. We covered 1-to-0-1 and 1-to-1. Let's continue with a multiplicity that we know well, multiplicity 1-to-n. So suppose we have these 2 classes, painter with a name, a Boolean field, a bit field, contemporary, artistic movement, and nationality, and you have painting with a title, with a support base. Could be canvas, glass, paper, with a medium that was used, oil paints, acrylic paints, and so on, and the width and height. And you have a painter with 0 or more paintings, but a painting that belongs to exactly one painter. Yeah. So here you see George Löwendal, who sits running Bukovina, and here we have Peter Bruegel the Elder with winter landscape with skaters and Bertrand, yeah, and the Netherlandish proverbs. So we know that we create 1 table per class. We'll have painters and paintings with their IDs, yeah, as primary key. So ID, name, contemporary, o să scriu prescurtat, artistic movement, and nationality, and paintings with ID again, yeah, with the title, with the support base, with the medium, with the width and height. And I'm using again this convention painter, so the singular of this table name followed by ID. one to many. So one table per class, and the key of this, let's call it one table. Let's say this is the one table, will become a foreign key in the second table. So if you also add a not null constraint here, not null, because we know by default foreign keys can be null, can take on null values if they're not part of the primary key, which is the case here. So if you also add a not null constraint here, then this means a painting belongs to exactly one painter, whereas a painter can have a 0, so he's still trying to get through and everything. 0 paintings that have been, I don't know, sold or more. Yeah. All right. So this is a one-to-many. Then we have this many-to-many multiplicity with WordPress sites with a URL and a profile like education industry, and the plugins that are used in these sites. So in which case you would create one table per class and an additional table, the join table. So I'm going to have here a WordPress sites table with an ID, the primary key, URL, and profile. And I'm going to have plugins. I should have used the singular over there, plugin. So I plugins here with an ID, the key. So I have the name, the creator, and the current version. And then I have this join table, which I'm going to call WordPress sites plugins, yeah, with the WordPress site ID and plugin ID as foreign keys together, forming the primary key of this table. So here it makes sense. We can use as a name for this one, we can concatenate the names of those tables or of the classes, or if this association is labeled, we can use the name of the association. And this is a good primary key here, because we're saying, okay, I just want to record the fact that a plugin is installed on a particular WordPress site. But if you want to store a history, like maybe someone installs and uninstalls and then installs again, then you would have to add a surrogate key here. All right. Now another many-to-many association, but this time an association that also has an association class. Let me just move on to the next one so that we can see the classes. Okay, we can see the classes and we continue with them, and then with inheritance, I think. Then with inheritance after a short break. All right, I think you can hear me now. So right before the break, I said we'd continue afterwards with a many-to-many, with an association that has a multiplicity many-to-many, and that also has an association class. This is similar to those like attributes that we saw were associated to relationship sets in the entity relationship model. So here we have two classes, data mining algorithm and research paper mining algorithm with a name, with a description and the type. Could be a black box, for instance, and the research paper with a title, an year, and a DOI, digital object identifier. And in such a paper, you can have experiments, experimental studies, and then you run experiments and you have some results that you present, you discuss in your paper with graphs, with tables, with discussions, with text, and so on. So in such a paper, you could use a data mining algorithm let's say more than once for different experiments. Of course, an algorithm could be used in different research papers. So in this case, we'd have data mining algorithms class with this surrogate ID, name, description, and type, and this research papers table with an ID, the primary key, title, year, and DOI. And in this case, I'm going to choose to, we know, for many-to-many, you have to create this join table, like we did before. So for this table in particular, I'm going to choose to name it, I'm going to choose to give it the name of the association class, but I'm going to use the plural again, so experiments. And for this one, I'd like to use a surrogate key, so that we gave examples of join table without and with a surrogate key. And then we'd have a data mining algorithm ID and a research paper ID. So I have a one-to-many and I have a one-to-many. And also this attribute from the association class results, which becomes an attribute in the join table. So in this design, this means that a data mining algorithm can appear in a research paper, can be associated with the research paper multiple times. Let's say once per experiment. All right, so we covered 1-to-0-1 and 1-to-1, and we saw that we can use one table, which is good because this means we have all the data in a single place. And if we have queries that require all the data, like we had students and DB lab topics, if you want data about a student and the topic that they chose, you don't have to do a join, right? Joins are expensive. But we also said that if you have queries that select only a subset of the data, that is a subset of the columns, like we had in individuals and DNA, which we saw as a one-to-one, and then we created a single table. If you have queries that often select only columns from DNA or only columns about the individual, then it does make sense to create two different tables, as more rows from those tables will fit in the main memory when you get the data from the disk. Okay, so 1-to-0-1 and 1-to-1, and then we saw 1-to-many and many-to-many, but also with an association class here. So for this one, we do need a separate join table. Now we continue with inheritance. Okay, so let's suppose that we have to model rides and roller coasters and boat hire points. Now, rides in this game had We'll have a lot of different things, but let's only take for this example the name of the ride, the price of the ticket, and the construction cost, the cost of constructing the ride. And suppose we have two subclasses, roller coasters with maximum track slope and the maximum height. So a roller coaster has a max track slope, max height, but it also has a name, a ticket price, and a cost, it being a subclass of ride. And then I chose the boat hire point as a second subclass with the number of vehicles, the vehicle type, like we could have rowing boats or other types of vehicles, and the maximum type a user was allowed to a visitor, a guest was allowed to be on that ride. Now, one approach that we can use is to build one table for each class, one for ride, one for roller coaster, and one for boat hire point, and then create a view for every pair superclass, subclass. So a view for the pair ride roller coaster and a view for the pair ride and boat hire point. And we're gonna do just that one. So I ride with name, ticket price, cost, roller coaster, max track slope, height, and boat. Sau dacă nu ne întoarcem înapoi și gata. Dar cred că I think I need to create, yeah. I'm gonna add here a new slide, so maybe one more. And maybe one more ca să nu înghesuim. Okay, so let's take this one. Okay, so I'm gonna do the first table, the one for rides, so name, ticket price, and cost. So I'll have rides with an ID, the surrogate key, name, ticket price, and cost. And let's start with roller coaster. So roller coasters. With max track slope and max height. And instead of adding a separate primary key here and a foreign key to rides, we're going to add a ride ID that is both the primary key and a foreign key referencing ID in rides. So then you obtain what you obtain here is a 1-to-1. You have for a particular row in rides with, I don't know, ride 1, you have the name, the ticket price, you have the cost. And then if you have a row with the same ID, 1 in roller coaster, here you have for this ride, for this roller coaster, the max track slope and the max height. And the same goes for both higher points. With a ride ID, which is again the primary key and a foreign key referencing ID in rides plus number of vehicles, vehicle type, and max time. Okay, so number of vehicles, vehicle type, and max time. Now, you have these tables in your database and you want an easy way to retrieve all the data about roller coasters, and then you can filter it or perform aggregations or whatever. Or you want to retrieve an easy way of retrieving all the data about boat hire points. So let's take roller coasters. You can create a view. For instance, roller coasters complete, that is, give me the complete information about all the roller coasters as, and here you simply have a join. You would select, from rides, and you have inner join. O să scriu IJ, bine, ca să nu, da, degeaba pe tot. Inner join roller coasters on ID equals ride ID. And we'd take what? Well, we'd take from rides all the columns. So we have ID, name, ticket price, and cost. And from roller coaster, we'd take max track slope and max height. And then by selecting from this view, we get all the data about all the roller coasters. And similarly, we'll create a view for both higher points. So the cool thing about this approach is that if you have to add other subclasses here, and this is the most flexible approach, as the current tables, the current views that you have are not impacted in any way. You simply add, so you have another subclass here, and then you add another table and another view. However, you can have performance problems because whenever you need all the data about a particular type of ride, you have to do a join. So it really depends on the cardinality of your tables and also on the physical structure of your database, on the indexes that that you have. So this would be a first approach. Now let's look at a second one in which we'd simply create a single table for the superclass, so for ride, and to this table you would add all the attributes of all subclasses. So in our case here, okay. So in this case, we'd create a table called rides with an ID. So this would be the primary key, and then we'd have all the attributes in the superclass. So name, ticket price, and cost. Name, ticket price, and cost. So these come from the superclass, plus all the attributes in roller coasters. So max track slope and max height. Was screen by inch? No. Max track slope and max height. So these are from roller coaster. And then from both higher point, number of vehicles, vehicle type, and max time. So number of vehicles, vehicle type, and I said yeah, max time. So these come from from about higher point. Oh, sure. Okay. Now, optionally, you can also create a table with information about your subclasses, and then a view for every subclass, so that you are able to easily find all roller coasters or easily find all boat hire points. You don't have to go to the table and check okay, which are the rows for which MTS and MH is null. It's those rows that are boat hire points, and vice versa for roller coasters. So you could go and you could create another table. Let's call it ride classes. Okay, hope you can hear me. I got a blue screen here, so I'll share again.
Yes, it's okay.
Man, I lost everything. Okay, not last time. Okay, so I was saying that in this approach, we create a single table. So it would be rights. I'm not gonna write everything again. I'm just gonna say that we had the ID, yeah, of the right, and then we had all the attributes in the superclass, and then yeah, so this one, the attributes in each subclass. And what I was doing when that happened was that I was creating this right classes table with an ID, and I wanted to also add this name column, and then to this table in which I'm storing all the attributes of the superclass and each and every subclass, I will add a foreign key, a right class foreign key referencing ID in right classes. And then here in this one, you can have something like one null or one unknown, 2 roller coaster, 3 boat hire point, and so on and so forth, an ID for each and every subclass. And then you could create a view to retrieve, for instance, all the data about all the roller coasters. You would create a view, again, roller coasters complete as select from rides where ride class ID equals, so it's this one, is 2. And I would select what? The ID. The ID. What did we have? Name, ticket price, cost. Ticket price, cost. And all the attributes in the superclass and all the attributes in the roller coaster subclass. Yeah, that is max track slope and max height. Am scris pe scurt, da? Acum știm, we know how to create views and stuff, and we know how to write a select from where. Now, usually this one gives a very good performance because you don't need joins to take data, for instance, for all the roller coasters. You have a select on rides. However, what's the issue with this approach? When you add a subclass, this structure that we created, this stable rights, has to be changed, right? You have to add the attributes corresponding to the newly added subclass. One more observation here, of course, all the attributes that correspond to your subclasses must be nullable. They must be nullable. For if not, this means that in a particular row you'll have data about the max track slope and number of vehicles. And in this case, at least these two sets here are disjoint. You don't have a roller coaster that's also a boat higher point, or vice versa. So this is approach number 2. And we have another approach, a third approach, in which we'd just go and we'd create one table per subclass. So before we created one table for the superclass and we bundled everything in there. We took all the attributes for all subclasses and placed them in that table. In a different approach, we'd create one table per subclass, and we'd add the attributes of the superclass as fields in each of the created tables. So in our case, this means we'd create a table called roller coasters with ID, and then we have name, ticket, name, ticket price, and cost. So these are the attributes that come from the superclass. And then we had max track slope and max height. These are the attributes in the subclass. Similarly, we'd have both higher points here with surrogate, the same surrogate ID. Again, name, ticket price, and cost attributes in the superclass, and the attributes of the subclass. So it was number of vehicles, vehicle type, and max time. So in this case, if you want to later add a subclass, that can be easily done. It does not affect, this operation would not affect any of the existing tables. However, if you have to change the superclass, such a change would impact all these tables. If you have to add an attribute or change it or drop an attribute, things like that. So each approach has its advantages and disadvantages. Okay, let's continue with aggregation and composition. Would have been a good idea to save it first, so that. Okay. Okay, so we'll now map. So we mapped associations with different multiplicities. We mapped inheritance, and now we'll map aggregation and composition. So in this case, I used a different multiplicity at this end here. So I'm saying written exam for a written exam, students will receive exactly 20 multiple choice questions. So, and again, a multiple choice question, it's aggregation. So if a written exam dies, its questions can survive, and they could be associated with different with different written exams. So I'm going to have, in this case, written exams with an ID, surrogate, and all the attributes that we have here: group, date, definition, and problem, and multiple choice questions. So we have MCQs with an ID and text and points. And then we could have written exams.
I'm sorry, I think we are still seeing the old slide. We can't see what you're writing.
Okay, hold on a sec. Keep.
Now we can see.
Yeah, just
okay,
can you see now?
Yes.
If I'm drawing. Okay, yeah. Thanks. Okay, so we have a written exam and multiple choice question. We saw this association before, only that now I was saying I use this multiplicity, okay, of 20. And I was saying the multiple choice question can continue to exist and be associated with other exams if the exam dies. So I created a table for written exam here. I use the same conventions and everything that we discussed so far. So I have written exams as the name of the table. I have ID as the surrogate, and then all these attributes here, which I assume are simple attributes, so they become fields in my table. And the same for MCQs with an ID, the surrogate, and these two attributes. So we got to this part where we implement, we create a joint table among these two with written exam, let's say written exam questions. We could name it like this, and we could have a written exam ID and a multiple choice question ID. I would normally say written exam ID and multiple choice question ID by the convention that I use. But the point is right now I'd like to move on to the next one. So that's why I'm using as attribute names only their initials, okay? But in the lecture notes, you'll have full attribute names. So here I would say written exam ID and multiple choice question ID. Okay, and I could say that a multiple choice question appears in a written exam exactly once. So I'm going to have this combination, this primary key. And if I want to, this is not mandatory, but if I want to like number the questions to see that they are, I don't know, really 20, or if I want to order them, if there's an order in my exam, I could also use an additional attribute named name position, but it's not mandatory. It's just something I would use to ease things for me. So this would be aggregation. if a written exam dies, yeah, all its multiple choice questions can continue to exist, and they can be associated with other exams. Now let's see how we can map composition, yeah, which is that stronger version. I have composition among multiple choice question and so same attributes and answer, an answer having a letter and a text. An MCQ, I'm saying here, can have exactly 4 answers and an answer belongs to an MCQ. If the MCQ dies, all its answers die with it. So in this case, a possible approach is this one. You have an MCQs table with ID, surrogate primary key, and text and points, and you have an answers table with ID, surrogate primary key, letter, and text, and as a foreign key, you have the MCQ ID, which means you could add here an on-delete cascade, right, for this foreign key, so that whenever an MCQ is removed from the database, all its answers are removed as well. However, with this approach, you cannot really say that an MCQ has exactly 4 answers. An alternative approach would be to have, right like this, MCQs, to have this table with, again, ID, text, points, and answer, let's say answer 1, okay, ID, answer 2, ID, answer 3 ID, and answer 4 ID. And asta e într-o zonă așa de no man's land. And then all these will be foreign keys referencing ID in answers. So I'll have something like this: 1 too many, 1 too many, and so on, or these 2 as well. So then a question is guaranteed to have 4 answers, but if a question dies, the answers don't die with it. You have to add code that does this, maybe via triggers. Okay, now let's see how we can map reflexive associations like this one that we talked about before, in which we model that hierarchy in an organization, in which an employee can be a supervisor for 0 or multiple other or other employees, for multiple employees. At the same time, an employee can have at most 1 supervisor, so 0 or 1 supervisor. You can accomplish this with a table, employees, with ID as a surrogate primary key. And the name, we said the address would be like a composite attribute, so I'm going to use an address ID here. The profession, and then we could add an attribute, manager ID, which is a foreign key referencing ID in employees. Yeah, so that you can have something like employee ID 1 with manager null. This is the CEO. Employee ID 2 with manager 1. Employee ID 3 with manager 1. Employee ID, so 2 employees, same manager. Employee ID 4, manager 3, and so on and so forth. You can create such a table. I'm going to talk about SQL Server specifically, but be careful if you try to create this foreign key with the option on delete cascade, it won't let you. It will say that introducing this constraint, this foreign key constraint, may cause cycles for multiple cascade paths, and you're advised to switch to the default no action option for foreign key. So you can do it, but not with an on delete cascade option. Now let's see another example. Whoa. Okay, so I guess I don't have it. Let's see another example of a circular dependency. Yeah, I like to keep them. A circular dependency, but this time with 2 different tables. I'm gonna go with, because we already saw questions and answers, so I'll work on them. Suppose, but on a simplified version. Okay, question with question ID and maybe other attributes, and answers with answer ID, and again, maybe other attributes. But the important thing is that in answer, I have, just like before, I have QID, yeah, the foreign key referencing QID in questions, and in questions, I'm also adding a correct answer ID. So, okay, a question has multiple answers. One of them is the correct answer. So, I wanna add this information to the database in this fashion, in this way. So this one would be a foreign key referencing AID in answers. So you could create this. You could create first the questions table. Again, I'm talking about SQL Server specifically right now, without a foreign key. Then create the answers table with a foreign key. There is a primary key to reference, and then you can alter this table questions, and you can add the foreign key on correct answer ID referencing AID in answers. But if you then have something like this, suppose you have in questions, suppose you have question 1 with correct answer ID, I don't know, 2, and then in answers you have answers, I don't know, 2, 3, 4 with question ID. With question ID 1. Now, if you try to delete this question from questions, you'll get an error, saying that the delete statement completed with the constraint and so on. If you try to delete this answer from answers, you'll again get an error, saying that the delete statement completed with the reference constraint. So you must first drop a foreign key constraint and then perform the delete. Moreover, while you are able to add this foreign key here to this column, and then once these two tables exist, add this foreign key referencing this table, and you can specify one of them to be on delete cascade. You cannot specify both of them. It's the same thing that we saw here. So you cannot have two such foreign keys referencing the other table. So this one here referencing this one, and this one here referencing this one, both of them implemented with on delete cascade. You get again something like introducing this FK constraint may cause cycles or multiple cascade paths, and you are again advised, you are told to specify no action, that option that we have, and this goes for both for on delete and on update. Alrighty. Okay, so great. We have 14 more minutes. So I would like to take a look at another another problem with you guys. So we'll see how much we can do. Let me open the board and I will reshare everything. Okay, so can you see when I'm switching between these?
Yes, we can.
Okay, so let's do another database together. We have this website, astronomyforbeginners.ro, which is powered by a relational database containing data about astronomical objects and phenomena. You are asked to design a part of the database schema and answer questions using the specified database language. Why is it a part of the data? Practical test or written exam or whatever, it's limited in time, right? It's 1 hour and 20 or 1 hour and something, or 2 hours in a normal context, so you cannot create an entire database schema for an entire website. Okay, so let's see. A natural satellite has a name and orbits a planet, and a planet has a name, belongs to a planetary system, which has formed around a star and can have several planets. Okay, so let's start with natural satellite and planet. What relationship do we have among these two?
So one to many.
Okay, so I'm gonna write satellite here. Satellites and planets. And I'm going to say an ID here and an ID here. And let's see. So, no. So satellite, a name. Okay, a planet. Okay, again a name. And what foreign key do I have to add to which table?
Planet ID for the satellite.
All right, so PID here, right? So, hai să mergem, dacă am început convenția asta, mergem chiar până la capăt. So I have a planet ID here, right? So I have a one-to-many. So which means a planet can have multiple satellites, but a satellite belongs to a planet. Now, if it orbits exactly a planet, we would add a not null constraint here. All right, let's see what's next. So it belongs to a planetary system which has formed around a star. Can have nu știu ce. A star has a name, age, and metallicity, real number, and it belongs to a galaxy, okay, and can have a planetary system. So what should we create now? What should we add now? What's the next table that we should create?
Star and the planetary system.
Star, okay, do we need both of them? So let's see, a planetary system has formed around a star and can have several planets. Okay, now a star belongs and can have a planetary system. So if a star doesn't have a planetary system, then it won't have any planets around it, right? If a star does have a planetary system, it will have all the planets in that system. Do we have attributes related to the planetary system alone?
Not really.
No, not really. Moreover, a planetary system belongs to exactly one star, and a star can have 0 or 1 planetary system. So at least now we can ignore this planetary system, and we can go and we can create directly the star table. And then what relationship will we have between planet and star?
One-to-many.
One-to-many, because we are told a planetary system can have several planets. So if the planetary system is for one star, this means the star can have several planets, but a planet in particular belonging to a single planetary system which is associated with a particular star, a planet can belong to at most one star. Yeah, I'm saying at most because you can have, I recently read about the planets, so planets near black holes. Or that, okay, nu despre asta aici. Okay, so let's continue then with stars. No. Stars with an ID and then name, age, metallicity. Name, age, metallicity. And then I'm gonna add what foreign key to which table to represent the relationship among planets and stars.
Star ID on the planet.
Okay. And then this corresponds exactly to our problem here. Yeah, a planet belongs to a planetary system, which is actually associated with a star. A planet belong, let's say by transitivity, belongs to a star. Yeah, if a star does not have a planetary system, so it does not have planets, it simply won't appear here. Its star ID won't. Star ID. Star. Its star ID simply won't appear here. But if it does have a planetary system, it can have multiple planets. It can appear in multiple rows here. All right. Then we were told that it belongs to a galaxy. Okay, and a galaxy has a name, diameter, category, elliptical, spiral, irregular, mass, and belongs to a group of galaxies or to a cluster of galaxies. And the galaxy can contain a large number of stars. Okay, so
Again, one too many.
Again, a one too many. So I'm going to add the galaxies table here with, again, an ID and name, diameter, category. Now, this one's a bit, because I'm told category like elliptical, spiral, irregular. So if I only have 3 categories, or okay, how many categories can I have? 3, 10, 20, 30, 100. Okay, I can use a tiny int, yeah, or maybe a small int, but I think a tiny int would be more than enough. So that means only 1 byte for the category ID. So if I have 100 galaxies that are irregular, I'm not going to say irregular, 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 and so on and so forth. I'm going to give its ID, so it's one byte integer. So I'm gonna choose to create another table that is categories. I'm going to do it here because it's not used later, so it's really a secondary issue. So with an ID, and I'm going to say, okay, I'm going to say a name here, yeah, for that irregular thing. And then this means that here I have, in galaxies, I have the category ID. We don't want too many, and then we had the mass of the galaxy, and okay, and a star belongs to a galaxy, and the galaxy has a large number of stars. So we have to add what foreign key to what table?
Galaxy ID to star.
All right, galaxy ID here. So it's a one too many. And now let's see next. So a galaxy belongs to a group or to a cluster. Okay, so let's see. A group of galaxies has a name, a diameter, and a mass, whereas a cluster has a name, a mass, and a type. That is an integer number between 1 and 3 as defined by this classification. Now, groups and clusters of galaxies can contain large numbers of galaxies. So we have again one too many here. Yeah, a galaxy, if it belongs to a group, okay, it belongs to exactly one group, and that group can have several galaxies, and the same goes with clusters. We're also given an example here. For instance, the Sun would be a star in the Milky Way galaxy. Now, this one in turn belongs to a galaxy group, so not to a cluster, called the local group. And the Earth is part of the Sun's planetary system with a single natural satellite, that is the Moon. Okay, so let's see this last part here. How would you approach this part? Now, a galaxy belongs to a group or to a cluster. Now, each of them have some parameters. We have name, diameter, and mass, and we have name, mass, and type here. How would you go about this one?
Can we use instance here?
Yeah, definitely. So then how would you do it?
Something like implement a group where
Okay.
it has the common part like name and mass, and then we extend that in a more complete group where we add the diameter, or a cluster group
where we have the type. Okay, I'd go with this one. Okay, I'd go with this one too. I'm having difficulties finding a name for this superclass, so I'm going to say it could be maybe an accumulation of galaxies. But I don't know if you know astronomy very well. Maybe that refers to the actual to the actual accumulation, nu știu, deplasarea galaxiilor. So I'm going to go with something that's simpler. I'm simply going to say cluster or group, okay? So, or something like G or C of galaxies. That would be the superclass, and that indeed contains the common attributes. So it could be a good approach here. Why is that? Because a galaxy belongs to one of these two types of, let's say, groups of galaxies. So then this means that in galaxy, I could have a single foreign key referencing the primary key of this table that corresponds to the superclass. And then I have those tables containing the attributes of the two subclasses. Now, alternatively, you can go and you can create two different tables, one groups, one for clusters, but then this means here you would have two different foreign keys, right? And one of them should always be null. So I'm gonna go with the approach your colleague just said. So I'm gonna say, okay, I'm gonna say G or C of galaxies with an ID, or if I'm using this convention, I can simply say ID. And the common attributes, one more time, were so name and mass. Okay, so we have name and we have mass here. And then here I'm going to have the group or cluster ID. So I have a one-to-many. All right, and then I have those two tables. So I have groups with by our convention, the convention that we used today, with a group ID, primary key and foreign key, referencing ID in GRC of the galaxies. So I will have a one-to-one here. And the other attribute was for group diameter, yeah, and clusters. with a cluster ID, and the type, right? Yeah, the type. So I'm gonna have one-to-one here. Now, if you get something like this for the at the test, if you have a problem with inheritance, like you have like the text of a problem with inheritance, you can choose any approach that you want, because we're not going to give in the text of the problem information about the cardinality of the tables or the existence of those indexes, so that you can have a well-justified answer saying, okay, I choose alternative A1 because, or I chose alternative A2 because, or A3 because. So if you have inheritance, any of the three approaches that we saw today will do, okay? Any of them. You don't have to justify that part. Alrighty, so yeah, this means that's about it for today. Yeah, I'm gonna take a short break, and then I'll be here to answer your questions. Just send me a short message on Teams. Next Wednesday, we have the practical test at 12 o'clock on Teams. Yeah, each of you will be, let's say, managed to be by your lab instructor. You'll take the practical test with your lab instructor. She's the one who will grade your paper. Please check that announcement on the website of the faculty. You are asked to turn on your camera for the entire duration of the practical test. It's an open book test. So for the practical test, you can work with the lecture notes, the seminar notes, your labs, with the online documentation. What you should not do is talk to other people. So just, be fair, and we'd like to see that what's there. It's what you came up with during the test. One more thing. So this week during my lab classes, I'm doing another model, let's say, for another big problem for the practical test. So I'm gonna upload that one, or I'm gonna send it to you, I don't know, as well. Okay, so săptămâna asta mi-a fac încă o problemă pentru practic în timpul orelor de lab, so o să o pun și pe aceea. Bine, numai să știți că de aceea nu o cunoașteți, că nu, deci o fac la laborator, ore pe laborator, dar o să o pun pentru toată lumea sub o formă sau alta, dacă doriți să vă mai exersați. No bun. Take care. That's about it for today. I'm waiting for questions. Și da, în general, I'm waiting for questions. Da, să începeți, vă rog, să învățați pentru examenul scris. Okay, please start preparing for the written exam, and I'm waiting for questions and stuff like that. But we'll talk more about this one during the next lecture, the last lecture. Okay, so take care, everyone. Bye.
Bye bye. Have a great day.